Here we have a position versus time graph for an object that we can use to define this idea of instantaneous velocity and instantaneous speed. So our object starts here, and we see that it moves in the positive x direction over this part of time. At this point here, we see that it's been moving in the positive x direction, but then it turns around and is now moving in the negative x direction during this time. From this moment, it turns around again and is moving back in the positive x direction. All right, so let's look at, say, something we already know, the average velocity between a couple different points. We could take the average velocity between this moment, call it t1, and say this moment way over here, t2, and we know that to find the average velocity, we would draw the line connecting those 2 points. And then measure the slope of that line, and that would give us the average velocity between these 2 events. We can see that it is a positive slope, a kind of small positive slope for this line, meaning on average, the velocity of the object between these 2 events is a small positive number. It's a positive velocity. It's moved in the positive x direction overall from here to here. Now, this line is not a very good representation of what the object actually did. I mean, it actually moved in this big loop here, moved way in the positive direction and then backwards in the negative direction some. So part of this positive motion was canceled out by part of this negative motion. So overall, on average, it's a very slight positive average velocity. Okay, let's imagine looking at 2 points that are closer together. Take these 2 events and sort of slide them together here. And what about the average velocity between there and there, between these 2 events, these 2 moments in time that are closer together? We would draw a dotted line connecting those 2 events. I'll go ahead and make it a solid line. And the slope of this line tells you the average velocity between these 2 events. And we see that's a larger positive slope, so it's a larger positive velocity between these 2 events. This line is a little closer to the actual curve of the object, but it's still just an average. Let's look at 2 points even closer together, say here and here. These 2 events, and draw the line connecting them. Okay, now this average velocity is an even larger, more positive value, and it actually looks pretty close to the black curve right there. There's not much difference anymore between the black curve and the average, compared to the huge difference between this black curve and this average. So as your 2 events get closer and closer together, your average becomes a better approximation of your actual motion curve. Let's imagine sliding these 2 points together until they touch. Let's imagine 2 events that get so close to each other that they become just one event. What happens to your average velocity when you're looking at a single event right here? This line, the connecting line between those 2 events, as those 2 events become one event, becomes what we call the tangent line to the graph. I want my line to just barely touch the graph right there. I'm going to cheat a little bit. There we go. As these 2 events get closer and closer together, they approach a single event, we can draw in this tangent line, a line that just touches the graph at that one moment. We'll call this moment t naught. So at this one instant, we're not looking at the difference between 2 events now, but we're looking at one single event. This line that just touches the graph, the tangent line, we can measure its slope. It looks like, let's see, there's the delta x, there's delta t. for my tangent line. And what we say is that this new quantity, the instantaneous velocity, the velocity at this one instant, one moment in time, which represent by the letter v, is the slope of that tangent line on our position versus time graph. So the slope of our tangent line tells us the velocity at that one instant. So for example here, at our time t0, our instantaneous velocity, and usually we just say velocity, we drop the word instantaneous, is given by the rise over the run, the delta x, the rise over the run, delta t, of this tangent line, the line that just touches the graph right there. Delta x over delta t of our tangent line. And by I, it looks like we go up about 4 meters, and our run in time about 6 seconds there. Alright, so that's about 0.67 meters per second. From looking at this position versus time graph and looking at this tangent line, we can determine the velocity of the object at that one instant. About 0.67 meters per second. Instantaneous speed is a very simple idea. At one moment in time, our instantaneous speed, we just say that's the absolute value of the instantaneous velocity. Speed is the absolute value of the velocity, which is exactly what your speedometer in your car says at a moment while you're driving. There's no positive or negative value on your speedometer. It doesn't tell you what direction you're going. It just tells you the rate. So instantaneous speed, just the average value of the velocity. No more complicated than that. All right, let's look at some other motion curves. Okay, here's a position versus time graph for another moving object, and I've marked a number of events while that object is moving, and let's draw in the tangent lines at each of these events. Here at the first event A, our tangent line, the line that just touches the graph, barely at A, is pretty much a horizontal line right there. At B, the line that just touches the graph, I'm just going to draw the line segment. I'm not going to draw a whole line across the page for each of these. At C, if we want a line that just touches the graph, maybe like that. At D, touches right there. E, we've got a horizontal line touching the graph right there. So these are our tangent lines at each event. All right, and we can look at the slope of these tangent lines to tell us about the instantaneous velocity at each moment. Well, the slope of a horizontal line right there is 0, so we know the instantaneous velocity at event A is 0. You see some other events on here with 0 velocity? Sure, right there. Velocity at point E is 0. It's a horizontal line, has a slope of 0. Our velocity at point I is 0, horizontal line. These are what we call turning points. They're places where our position versus time graph turns around. It's going up and then it turns back. So where it turns over, at the peak of that graph, your tangent line is horizontal, meaning at that one instant, your velocity is 0. Here at the bottom of this curve, this lowermost point where your tangent line is horizontal, there for an instant your velocity is 0. Here at the beginning we started from rest. Our velocity was 0, horizontal tangent line. The velocity at B here, clearly that's a positive slope here. So we can say that that's a positive velocity. Velocity at C is also a positive velocity, positive slope right here. D is a positive velocity, meaning at events B, C, and D, the object is moving in the positive x direction, which we can tell. At events F, G, and H, here we have a tangent line with a negative slope. So that velocity right there is less than 0. The velocity at event G also less than 0, negative slope right there at H. So between these two turning points, these two moments where the velocity is 0, it's positive the whole time. Then between these two turning points where the velocity is 0, it's negative the whole time. And here, beyond it, we see at j that we have a positive slope, so our velocity is positive once again. Let's make a comparison over here between events B and C. Positive slope, but which is more positive? Which is a steeper tangent line? Well, C is. That's a steeper tangent line than B. So we can tell just from looking at it without doing any calculations that the velocity at point C, at event C, is greater than the velocity at event B. We can compare those two by eye, by looking at the slope of the tangent line. How about over on this side? How does the velocity at point F compare to the velocity at event G? Negative slope here, but a steeper negative slope here. This looks like it might be -1 meter per second maybe. This could be -5 meters per second. So we can say that just from looking at it, the velocity at point F is greater than the velocity at event G. This is a more negative slope. All right, I'll try a few of these on your own. Here is another curve. Events labeled on it. I want you to take these, 7 events? 8 events? 9 events? Take these events and rank them from moment with the greatest positive velocity to the moment with the greatest negative velocity. So rank these events in order. Which one does the object have, at which event does the object have the greatest positive velocity? Where is its velocity less than that? And where does it have the greatest negative velocity? And where's the velocity 0? See if you can put all these events in order in terms of their velocity. Give you a moment, pause the video. Okay, ready? Let's just quickly sketch in our tangent lines at each point. This horizontal one right there. It's a very slight negative slope there. A steep negative slope there. Horizontal, slight positive slope. Steep positive slope. Sort of medium positive slope. And 0 right there. So from looking at these slopes, we see that we do have some turning points. There's B, where the velocity is 0. And also event E, where the velocity is 0. And event I, at the very end, we come to rest right here. At all of those, our instantaneous velocity is 0. Whereas at positive, between E and I, positive slope, positive slope, positive slope. Slightly positive here at F. So it's a small positive velocity. More positive here at H. There's F, there's H, steeper than F is. And G is the most positive of all, almost vertical. Very steep positive slope, moving very rapidly in the positive direction right there at G. Here moving slowly in the positive direction, moving slowly in the positive direction, moving very rapidly in the positive direction. How about over here? We're moving very slightly in the negative direction at C, small negative slope. We're moving a little more quickly in the negative direction at A, sort of a medium negative slope of about -1. And we're moving very quickly in the negative direction at D. Rapid movement in the negative direction, very large negative slope. Okay.